So as a practical setup, consider that there is a excellent wine company that wants to develop a machine learning model for predicting wine quality based on certain physiochemical characteristics of the wine. They want to use this machine learning model to replace the expensive quality sensor. Let us understand steps involved in addressing this problem. There are 8 steps in machine learning project. First, we look at the big picture. Then we get the data. We discover and visualize the data to gain insights. We prepare the data for machine learning algorithms. We select a model and train it. Then we fine-tune our model. We present our solution. And finally, we launch, monitor, and maintain our system. So generally, machine learning is a small piece in the big project. For example, wine quality prediction is a small piece in setting up the manufacturing process. We spend typically 10 to 15% time on machine learning setup. A lot more time is spent on capturing and processing data needed for machine learning and taking decisions based on the output of machine learning module. And we need strong collaboration with domain experts, product managers, and engineering teams for successful execution of machine learning projects. Let's look at the first step where we look at the big picture of the problem. Here, the first and the most important thing is to frame the problem properly. We select a performance measure, then we list and check the assumptions that we have made while arriving at the solution. As part of framing the problem, we need to figure out what is the input and the output. What is the business objective and how does company expects to use and benefit from the model. These measures or this kind of information is useful in problem framing. It is also useful in algorithm and performance measure selection. And it also aids in overall effort estimation. It is also important to understand what is the current solution because the current solution provides a useful baseline. Sometimes the current solution could be to use a human labor to figure out what is the quality of the wine. Now we can figure out what is the accuracy or what is the accuracy of the current system that is deployed for the problem. And we aspire to build a basic machine learning model that attains at least that level of accuracy as a baseline. And if we provide all the data that is available to this particular process, we hope to build a machine learning model that is likely to beat this particular baseline. Let's look at some of the design considerations in problem framing. We need to figure out whether the problem is supervised learning problem, unsupervised learning problem, or a reinforcement learning problem. You are aware of supervised and unsupervised learning problems from machine learning techniques course. So as part of supervised learning task, whether it's a classification or regression task or some other task, what is the nature of the output? Whether there is a single output or multiple outputs that are expected from the machine learning system. Does the system need to learn continuously or if the periodic updates are sufficient? And what would be the learning style, whether we'll be learning in a batch or whether we'll be learning in an online fashion. In online fashion, as the data is arriving, we are supposed to learn the model, we are supposed to update our model and use that updated model to make predictions. In the batch mode, we take a bunch of examples together in order to learn the model. The next part of the process is to select the appropriate performance measure. For regression, we use mean squared error or mean absolute error as performance measures. For classification, we have precision, recall, F1 score, and accuracy as performance measures. Next step is to check the assumptions that we make for solving the problem. We need to list down various assumptions about the task. We would like to review these assumptions with domain experts and other teams that plan to consume the output of the machine learning module. This helps us in making sure that all assumptions are reviewed and approved before coding. The second step of the process is to get the data. The data is usually spread across multiple tables, files, or documents with access control. We need to obtain appropriate access controls and authorizations to access this data. Then we generally get familiarized with data by looking at the schema and few rows. In this step, familiarity with SQL would be very useful. We first load the basic Python libraries that are needed for our prototype solution. Let's first access our data. In this case, we need to download this data from the web. It's a good practice to create a function for downloading and extracting the data. Here we download the data from UCI machine learning repository, and the data is in the form of a comma separated values or in a CSV format. Now that the data is loaded, we need to examine it. We look at a first few data sample with the head method. We simply call the head method on the data frame. The head method gives us first few rows or exactly 5 rows from the data frame. Here on your screen you see the first 5 rows in this data frame. The first row here shows the names of the columns of the data frame. In this case there are 12 columns: fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, sulfates, alcohol, and the quality. And the first row shows the values for different features for the first example. The second row has the values for each of these features for the second example. And the quality is the label that we are interested in predicting. So this is the feature vector consisting of 11 features, and this is the label Y for the first example, or specifically Y1. This is a label for the second example, third example, fourth example, and fifth example. And there are corresponding feature vectors that you can see on your screen. Once we have a data, it's a good idea to understand significance of each feature by consulting the experts. In this case, we have 11 features. The first feature is fixed acidity. The significance of this feature is that it captures most acids involved with the wine are fixed or non-volatile. These acids do not evaporate readily. Then there is the second feature is volatile acidity. It captures the amount of acetic acid in wine, which at too high of a level can lead to unpleasant or vinegar taste in the wine. The third feature is citric acid that captures. So citric acid is usually found in small quantities in wine, and citric acid can add freshness and flavor to the wine. The next feature is residual sugar. It's rare to find wine with less than 1 gram per liter residual sugar, and wines with greater than 45 grams per liter are considered sweet. Then chlorides, which is the amount of salt in the wine, and finally alcohol, which is percentage of alcohol content in the wine. So whenever you are solving a machine learning problem and once you get a data, it's a good idea to document the features and their significance by consulting the experts. So you can access the feature list from this data by accessing columns of the data frame. We print values of all columns but the last. The last column is the label. So you can see 11 features in the feature list and one label. And the feature list has got features like fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, sulfates, and alcohol content. And quality is the label that we wish to predict. Now that we have got a fair bit of understanding of the features, let's look at the data statistics. We use info method on the data frame to get the quick description of the data. So this particular description talks about various statistics about the data. There are 1599 total entries. So by going by ML standard, this is really a tiny data set. There are 12 columns, there are 11 features and one label. The label column is quality and the remaining 11 columns are the features. And you can see that all columns are numeric while the quality or the quality which is a label is an integer column. In order to understand the nature of numeric attributes, we use the describe method. The describe method gives us statistic about each feature. Or specifically, it gives statistics about each column in the data frame. So here you can see the statistics about fixed acidity. This is a number of examples for this particular feature, and the mean is 8.3 with standard deviation of 1.74. The minimum value of fixed acidity is 4.6 and the maximum value is 15.9. The 25th percentile is 7.1, 50th percentile is 7.9 and 75th percentile is 9.2. And you can similarly look at the statistics for other features. So as we just discussed, it prints counts and other statistical properties like mean, standard deviation and quartiles. The wine quality can be between 0 and 10, but in this data set, the wine qualities are between 3 and 8. Let's look at the description. Let's look at the distribution of examples by wine quality. So we simply call the value counts on the quality column of the data frame. And you can see that the wines of quality 5 and 6 are dominating the data set. The higher quality value implies better quality of the wine. And we can see that there are lots of samples of average wines than good or the poor quality ones. There are many examples with quality 5 and 6. This information can be viewed through histogram plot. A histogram gives the count of how many samples occur within a specific range. We use SNS or Seaborn as a plotting library. So you can see that wine quality is on x-axis and the count is on the y-axis. And we have plotted histogram of the wine quality. In this histogram you can see that the wines of quality 5 and 6 are far more than the other wines of different qualities. For example, wines of quality 3 are much lesser. Similarly, the wine of quality 8 are also far fewer compared to these two wine types. In the similar manner, we can plot all numerical attributes with histogram plots. So you can see histogram plots of different features here. And we have also included the histogram plot of the quality for your reference. The x-axis in this plot shows the value of the corresponding features and the y-axis is the count in that particular bin. So the values of the features are divided into a fixed number of bins and we count the number of values in each bin which is on the y-axis. So you can see that different properties or different features have different scales. Their values vary. So for example here the value of total sulfur dioxide can be between 0 to 300. In this case, the range of the total sulfur dioxide is between 0 to 300, whereas the density is between 0.99 and 0.99 and 1. Whereas pH varies from 2.8 to 4, sulfate varies from 0.5 to 2, and alcohol varies from maybe 0 to 14. So different features are at different scales and features have different distributions. Some of them are tail heavy like residual sugar and free SO2 and few have multiple modes just like volatile acidity and citric acid. Before any further exploration, it's a good idea to separate test set and do not look at it in order to have a clean evaluation set. When we look at test set, we are likely to notice patterns in that and based on that, we may select certain models. This leads to biased estimation on test set which may not generalize well in practice. This is called data snooping bias. Let's write a function to test the data. Let's write the function to split the data into training and test. Make sure to set the seed so that we get the same test set in the next run and in subsequent runs after this. So in this particular function we take the data and the ratio of test examples. We first set the random seed and here we have set it to 42. Then we shuffle the data set. Then we calculate the size of the test set and we split the data set to get training and test sets. So data set is shuffled with np.random.permutation method and then the shuffled indices are used to split the data into training and test. So in this case we have called this split train test method with the test ratio of 0.2. That means 80% examples will be used as training and 20% examples will be set aside for testing. Scikit-learn provides a few functions for creating test sets. Based on random sampling, which randomly select k percentage point, in the test set, or the stratified sampling, which samples test examples such that they are representative of overall distribution. The train test split function performs random sampling with random state parameters to set the random seed, which ensures that the same examples are selected for test runs across different runs. The test size parameter for specifying the size of the test set, the shuffle flag to specify if the data needs to be shuffled before splitting. It also has provisions for processing multiple datasets with an identical number of rows and selecting the indices from those datasets. This is useful when the features and labels are in different data frames. So the train test split function is in sklearn.modelSelection library. So we import it from sklearn.modelSelection, import train underscore test underscore split. So whenever we come across a new function, there is a good chance that we are not aware of all the parameters. While we have listed some of the key parameters of this particular function, there may be some more parameters that you might require in certain typical situations. So you can use question mark followed by the name of the function in order to read the documentation of this function. So before calling for the documentation, make sure that you have imported the API or the function from sklearn library. So when you try to access the document with the question mark command, the document opens and it shows a different kind of parameters and the doc string of this particular function. So let us apply the random sampling to our dataset to split it into two sets, training and test. Here we set aside 20% examples for the test set. So whenever the data distribution is not uniform, we use what is called as stratified sampling. Random sampling introduces biases in the non-uniform datasets. So in our wine quality dataset, the label distribution in our dataset is not uniform. The labels of type 5 and 6 are far more representation than the other types of label. In this case, the label 5 and 6 are overrepresented in the datasets, whereas other labels are underrepresented in the dataset. So the distribution of the label is not uniform. And this could be a problem for random sampling. And the problem would imply that the test distribution may not match the overall distribution. So how do we sample in such cases? So we divide the population into homogeneous groups called strata. Data is sampled from each stratum so as to match it with the overall data distribution. Scikit-learn provides stratified shuffle split class that helps us in stratified sampling. So the stratified shuffle split is also present in sklearn.modelSelection. We need to provide the number of split, the size of the test set, and the random state, just like the train test split function. Let us examine the test set distribution of the wine quality that was used for stratified sampling. and we'll compare it with the overall distribution. Let's look at them side by side, and we can notice that there is a small difference in most of the strata. So in this table, we have the overall distribution of different wine types. So these are the wine types: wine type 5, 6, 7, 4, 8 and 3. This is the overall distribution in the training set. 42% examples come from the type 5, 39% examples come from type 6, 12% examples come from type 7, 3% comes from type 4, 1% from type 8, and less than 1% or 0.6% examples come from type 3. And when we perform stratified sampling, you can see that the overall distribution of the data is maintained. Here, as against 0.42 or 42% examples of type 5 in stratified sampling, we get 42% examples from type 5. In other cases also, you can see that the overall and stratified numbers are very close. So in the third column, we have represented the difference between stratified and overall distribution. And the last column provides what is the percentage difference between overall and the stratified case. So the difference is pretty small, and you can see that even in terms of percentage, the difference is minuscule in many cases, except for this particular case where the difference is about 16.71%. Let's compare this with random sampling. So when we compared the overall distribution and the distribution obtained from the random sample, you can see that there is a large difference. So this difference is about 4.6%, 3%, 5.4%. This is 39% difference and about 50% difference. So you can see that in smaller classes the difference is far more compared to larger classes. So you can see that the stratified sampling gives us test distribution that is closely matching to the overall distribution as compared to the random sample.